Welcome back. In today's video, we are going to be having a look at CPD Search. This is probably one of the first videos where there isn't an acronym for this algorithm, so that's maybe something to keep in mind. CPD Search, well, I mean the acronym CPD is already Compressed Path Databases, which is essentially a perfect distance heuristic. We're storing this massive table that tells us exactly where the first move is, where we need to go from every possible location to any other, right? So we've essentially compressed and stored this all pairs distance table. I have a whole video on CPDs if you need that background. Now, CPDs are essentially, right, like they're the leading heuristic. In static environments, they completely eliminate the need for real-time search at all. Instead of trying to actually search, all we have to do is we have all the first moves, so we've transformed the problem into one of simply retrieving the path from our CPD. Now, okay, so CPD search is going to be a very, very easy. This is essentially an anytime algorithm. We're going to be running search in an A-star fashion, right? We're adapting A-star to these anytime search framework. This is going to be useful for dynamic environments, right? So the requirements, kind of like the use case of where CPD search comes into play. Well, this is when, again, because we needed to have actually known the graph, the map, the actual problem a priori, well, we need to have this information such that we can actually construct the CPD from the get-go. Constructing CPDs is a oftentimes very, very heavy pre-computation step, right? As well, we're looking at dynamic problems. So every edge within this graph, or every movement, every action you can take, right, it has to have some form of base cost, okay? So we know we're going to be working in problems where parts of the map might become more costly, or even the actual cost can fluctuate, right, up and down. That's what this is saying. So edges can change their costs up and down, but the key idea is that the costs, well, they can never fall below this base floor. So I have actually done an exercise video to fully explain this. So if we don't have a base value, CPDs fall apart completely. So if you want to understand how that goes, I recommend go checking out that video. It's like 10 minutes of just, hey, here's a worked example. CPDs will mislead you, right? It's an inadmissible heuristic if things fall below this base cost. So we're working with, in this video, the idea that, okay, yeah, there has to be a base cost. The heuristic has to be using that base cost, the smallest the cost can possibly be for every action, for every edge in your graph. We're using that to construct a CPD, and we are going to be using that CPD to perform anytime search in these dynamic environments where things can be changing or could have changed between planning episodes. So essentially I have a very small worked example down here, just a very regular grid map. Well, what I'm trying to say is that the blue areas here, these are walls, right? So these were there in the initial problem as well when we ran the CPD. But in yellow I've drawn something like quicksand, right? Or maybe a forest or the area flooded, whatever it is. I'm essentially saying that the cost of these nodes have increased now, okay? So at this point, when I'm asked to plan the path from S to T, things in the world have changed. Your player has maybe messed with some things. These regions are going to be really costly to move through. Say they have a cost of 10, doesn't matter. The base cost of everything was 1. So then, I didn't bother to draw up the full CPD, but you have this thing, right, where it's an n by n table. So it'd be, it's not matching exactly, right? It's like every single node in this entire grid is the length of the table in both the vertical and horizontal. I've drawn a lot of dots, right? But when you go about retrieving the original CPD path, just to refresh our memories, what you're doing is you look for, hey, what current node are you at? Well, I'm at the start location S, okay? Then you look for the column corresponding to where you want to go. Well, the first move was previously telling us we just want to move east, we want to move right, because at the time it was a cheap cost. Now we know things might change. So this is where we're all coming from. What is the idea of CPDs? Well, this is, as I've been saying, an anytime variant of A-star that leverages the fact that CPDs give us two useful things. They provide both strong upper bounds and strong lower bounds. So that's the whole basis behind this idea. So CPDs give us not only a strong lower bound. Hey, this is the best optimistic way, right? If the costs were all the base edges, this is as fast as I can get there. That is going to be our admissible heuristic, right? We know when we're running an A-star search, we need our heuristic to be accurate, but it has to be admissible, consistent. Well, CPDs are. In the base cost, that is going to give us the optimistic estimate, our lower bound. If the lower bound and upper bound concepts don't make sense to you right now, please look at the previous video on this channel on anytime search and anytime weighted A-star, which is, I should have mentioned, that's a fundamental prerequisite for everything we're looking at here, okay? So essentially, yeah, we're now looking for an upper bound, okay? What is the upper bound? Well, the CPD, right, is giving us, we're able to extract essentially the full path that it's telling us to take. So the original CPD, well, it says go this way, right? This would be the path that we extract. We know that the cost of this path has changed now, right? There are these regions, these expensive regions the path's going through. Well, what we do is we just track this. So hey, the lower bound is essentially just the base cost of the CPD path. Right, so explicitly the CPD would have told us 1, 2, 3, 4, 5, 6. Yeah, the CPD thinks we can get there optimistically in 6 steps. The upper bound, which we're getting to, this is going to be actually just the real cost of the path, including the edge weights, right, that might have fluctuated and changed since our initial pre-computation using the base costs. You can see why the base costs are really important here. So right, essentially we see that there are 2 of these yellow quicksand regions you have to walk through. So obviously the upper bound is going to be substantially more expensive than another path. So realistically we see that the optimal path these days would take this longer, lower route, right, and it would avoid the high cost regions. Well, we'll eventually find that, and I'll show a worked example in a second. But the upper bound really is just the true cost, the real cost of the CPD path. So that's interesting, right? So we're abusing CPDs, and it's providing us really useful information in order to actually prune things from our search space. Similar to anytime weighted A-star, just this is anytime search in general. Well, all of our nodes, this time we're actually going to rank nodes in the open list just by their actual just f of n, right? So there's no more weighted functionality that we saw in maybe the previous video. So nodes are just still, it's regular A-star. They're ranked by f of n, so f equals g plus h. Well, we're able to prune any node whose f value, right, is greater than the cost of the best path we've found, okay? We're doing an anytime search. We're going to continue iteratively looking for improvements to our solution cost, right? We're trying to essentially prove optimality, and we can find, right, we know that we can find a better version of the path. However, again, anytime algorithm, you needed to find a first solution fast. Well, we did. The CPD provided us a direct, instantaneous, almost, hey, this is the path you should have taken. It has a suboptimal cost. We're going to improve it over time. We're using our upper and our lower bounds to constrict search until we can prove when they cross that we have indeed found the optimal solution. So let's maybe write up some stuff here just to add to this conversation. So as I said, nodes are ranked by f equals g plus h, of course, the standard A-star. Now, the other aspect of this, again, is that we prune nodes with f greater than our upper bound, of course. This is the idea of anytime search. And essentially, right, like the process of what we've been doing throughout the whole thing is anytime you expand a node for every successor and prime, right, we're essentially extracting their CPD path to create their lower and upper bounds. So for each successor n prime, extract the CPD path, which just looks like, right, from n prime dot 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 all the way to the target t. So this is quite exciting. CPDs are extremely easy to understand. Again, it actually looks pretty easy to implement, assuming you've already figured out how to create a CPD. Go look at that video. Now I want to cut across to future me to walk through an example of what this is actually going to look like. Okay, so let's walk through this very simple example I've drawn up here just to get used to CPD search. So what's the first thing we're going to have to do? Well, of course, we're going to have to do some form of pre-computation to create our CPD, our distance table. Now, in the ideal sense, of course, you don't know where your start and target is. You're going to do this for the whole map. You just have to do this once. Sure, it's a big ordeal, but then you're going to essentially collect all pairs distances, convert these to first moves, compress them somehow. Ta-da, we have our CPD. In the problem here, just because I have a single start and target, well, what I'm going to show you is the other version of this, which is equivalent. We're just going to run a backwards Dijkstra's from the target t to all reachable locations, and that is essentially going to be our distance table, right? It's storing the actual distance from any node to the target t. Well, the beauty is we're going to be abusing that distance table as an estimate, as a heuristic value. Remember, this is happening in our base cost world. You have to ignore the green region here. All the costs are just their standard of 1 for straights or root 2 for diagonals. Note that I am using diagonals in this problem. Okay, so here we see the backwards Dijkstra's now running, collecting all of this information. And essentially at the very end, we now have our distance table. We have our CPD now, and let's just take one step to return to the actual problem here. I think it's a bit easier to see this. So we have already this blue line from the get-go before we've even begun search, right? So our CPD has essentially given us from our start location, well, this is the path that we think you should take. This is the optimal cost in this base cost world. Well, that path has a cost of 11.24. So CPD search is going to be performing this A*-like search behavior, but where we're weaving in this anytime behavior in terms of our upper and our lower bounds in order to essentially prove optimality when they join together, and as well be able to prune nodes from the search space during search. Well, from the get-go, the cost of this blue path here, that is our lower bound. That is our optimistic estimate. It has a path cost of 11.24. However, as we've already discussed, CPDs provide us upper bounds as well, which is really nice. So what we do is we actually just trace along this path here returned, and we collect the true cost of the path. So in this problem, of course, we now have this green region. This is a region where perhaps there's a forest now, it's flooded. Whatever it is, the values of these regions are more expensive to walk through, right? So the actual cost of the path, which does go through this region, ends up being 15.16. This is our upper bound. This is the best path we've found thus far, and we are going to begin search now and obviously iteratively improve it and use it to prune things from our search space. Okay, so stepping into this, well, we begin as you would expect. We start generating candidate nodes. The difference here is, right, so the first one we're generating is D2, that's the yellow node here. We're drawing this grey dashed path. The grey dashed path here is again just the CPD recommended path according to those base costs. So we're using this as the heuristic, right? The actual distance of this path that it's recommending is our heuristic value. What's really interesting to note in CPD search is we'll start to see that these dashed lines, right, repeat a lot of the same ends of the paths, right? A lot of the different versions of the paths will already use information that we've already retrieved from the CPD. So up front, I just want to tell you something we can do is simply cache a lot of that information. So what is the path distance, or what are the moves from these locations onwards? And we can start to essentially get this amortized complexity of really just O of 1 for the path retrieval itself when we keep reusing information we've already seen. That's an aside. But let's continue the example here. So we start generating these other 4 children. Well, I think the first interesting one is now E3. So E3 is returning again to having, it's the first of the children that have the same F cost as the start node, right? It's the step in the correct direction. So we generate the rest of the children, but then we end up expanding E3 as our promising direction. So we start to generate some of its children, but we see that we're now stepping into the weighted region. So the cost is increasing here. We continue to generate a few more children, right? You have all of their paths. We expand some further nodes. We continue, so forth, so forth, so forth. Essentially, all of these paths are trying to increase the quality, but the CPD paths are interacting with the weighted region, right? So none of these are looking promising. They're all looking quite bad. This includes the path from E5. So I just want to know that the cost model I'm working with in these problems, well, similar to the idea of corner cutting, you can't just have an agent with size squeak past an obstacle, right? You're never allowed to take the diagonal across an obstacle because you're technically hitting it. It's similar with weighted regions. So whenever you're taking moves in or out of weighted regions or between weighted regions, essentially the cost model is just that you take an average of all of the weights of the tiles. So in this little square here from C6 to D7, well, that is 3 empty spaces, right? And one of them is weighted. So that'd be a cost of 3 plus 2, right? Because the weighted region is extra. You divide that by 4, you take the average of it, and then you multiply that by the square root of your diagonal move. Anyway, so I just wanted to note on the cost model, but it's not so important for this problem. This is handled automatically. So what we're going to do is we continue generating a few children until we get F5 here, okay? That's interesting. We've generated the child F5, and our blue path is updated. Why is this the case? Well, up until now, all other children have essentially not improved the actual path cost, right? Every time the heuristic CPD recommends a path, well, the actual cost has been greater than the recommendation. This is the first node we've generated that the grey path that we would have drawn is actually still the exact same cost as the real distance in the grid. So what that means is our optimistic estimate and the real distance are equal, and therefore we can say that the rest of the CPD path is a valid path. We're going to use that as a candidate solution. Is it better than the current one that we already found? Yes, it is. So in this case, we're going to be updating the upper bound now from our 15.16 to the new best cost solution, which is 12.92. Okay, so that's quite exciting. What this lets us do then is we start to see these other nodes here are able to be pruned. So this is the other advantage of these anytime search behaviors. We now have this new best solution, and we're looking at our open list and we say, well, these nodes, even in their optimistic case, could never improve things. So we're able to prune them from the search space and save all the heap operations that we would otherwise need to maintain. So we see here that they get dropped, and we're going to continue expanding some other nodes, looking for these alternate paths. We continue until we essentially generate a G4. Looks like we have another very slight improvement to the path. We're going to update the upper bound once again. We get to prune a node, and we kind of continue for a few steps until we finally generate F5, and we find a new best version of the path. Well, this new best version of the path has the exact same cost as the most optimistic path left in our open list. Essentially what this means is our upper bound and our lower bound have finally crossed, right? At this point in time, regardless of how many things are in open left, we can prove that this is an optimal solution. We have found an optimal solution. We get to terminate search. You can see all of these other nodes in open get to be pruned and thrown away. This, we're already seeing, as a bit of an advantage of CPD search relative to anytime weighted A star, which was the other anytime search algorithm I looked at in last video. Well, there you had to completely exhaust the open list. CPD search does not have to do that, right? The CPDs are providing these really, really nice both upper bound and lower bounds, which lets us directly prune things from the search space because these are optimal paths, right? There isn't this weighted suboptimal aspect entering into the equation. And ta-da, so we essentially do one extra step and then we get to prove that this is the optimal solution and we're done. So I'll flip here just to show you what the weighted terrain looks like underneath. Maybe this is helpful for visualization. But this is CPD Search. It's very fast and it has these really exciting properties of being able to handle changing weights and dynamic obstacles perhaps in environments, as long as that first CPD pre-computation is of course using the base cost. So it's interesting to see that CPDs give us both upper bounds and lower bounds that let us prune things in the search space and prove optimality faster. So let's jump back into the video. Okay, so now we understand visually how CPD search is working. I think it's pretty intuitive. It's a very easy transfer across of, again, these anytime search behaviors. So the last thing I wanted to note, just in terms of like the amortized complexity. So CPDs, I mean, a lot of paths, right? A lot of nodes have the same tail end of their paths, okay? So what we do is when we're starting to extract these CPDs, well, we may as well cache, right, some of that remaining paths. So when we're exploring a bunch of nodes, this is relevant for domains like grids, right? So certain other domains definitely won't have this strong overlap. But in grids, yeah, a lot of the end of the path will just look the same. So if we're caching that information, it means we don't have to go and extract that information from the CPD every time, which has this, right, for a path of length m, it will be m log n, because we have to do a binary search to find each one of the correct columns within the CPD. So we essentially transform that into kind of like O of 1, more or less, because, hey, we've already seen these information, we've cached it, so we never have to go look up the same information again. So that's something that also improves CPD search. Nonetheless, that has been CPD Search. I think it's a pretty easy and intuitive idea. This is extremely performative in dynamic environments. So yeah, when you're able to define this base cost, right, that's the key idea here. Well, then CPD Search and abusing CPDs really can transform itself very nicely. Even though we only calculated the CPD once before any of these changes happened, we get this really nice anytime search behavior, and it's extremely quick and performative in these domains. So this is definitely something I would consider adding to your toolkit. Okay, thank you for watching. In the next videos, we're kind of now transitioning away from, we've had a quick look at some dynamic environments. We're moving towards these advanced obstacles, right? So now we're going to start having a look at dynamic obstacles in terms of moving, in terms of time, okay? So we're going to start working with exploring search problems when in domains with time, with weighting actions and so forth. So this is, again, another whole avenue of search algorithms to have a look at. So please join me in the next few videos where we look at time-expanded A-star and safe interval path planning. Thanks and see you there.